This is STA 381, Chapter 2, Section 7. Okay, so now we're ready to talk about independence of events and some rules governing that. So we've talked about mutually exclusive events, and that's a type of dependence. If one event occurs, the other one cannot possibly occur. And so now we're going to be talking about independence, and that means that one event happening that has no bearing or effect on the other event. A really simple example of two events that would be independent would be, say, successive coin flips. You flip a coin, you get tails. That's going to have no bearing on the next flip. It could still have a 50-50 shot of being heads or tails. Whereas mutually exclusive events, one way to think about mutually exclusive events would be also in terms of, say, just one coin flip. So you flip a coin, if you got heads, you could have not possibly gotten tails at the same time. So just to give you a really simple example to go back to if you find yourself struggling with those concepts. All right, so let's go ahead and take a closer look and talk about event independence. Two events are independent if any one of the following equivalent statements is true. The probability of A given B is equal to probability of A. What that means is that B occurring does not affect A. Number two, the probability of B given A equals the probability of B. Again, same type of idea here. The fact that A occurred did not affect the probability of B. Or number three, the probability of A intersection B is equal to the probability of A times the probability of B. And again, all three of those are pointing to the same direction, and they really are equivalent statements. So let's take a look at this example from the text. Table 1 provides an example of 400 parts that are classified by surface flaws as functionally defective. Suppose that the situation is different and follows table 2. So let F denote the event that the part has surface flaws. D denotes the event that the part is defective. So one is flaws just on the surface. The other one is actually that the part is defective. Okay, so let's take a look at table 1 for a second. And we see a table that it's a little contingency table which is classifying these parts with either the surface flaws and or being defective or not defective. So just to explain it really quickly, this first box right here with the 10 that I just circled, what that means is that the part has surface flaws and is defective. So both of those are happening. So and then we have, various combinations there. So if you look down here at the probability of D given F, so the probability of defective given surface flaws. Well, the probability of defective given surface flaws, what that means is because we're given the surface flaws, we're only looking at that column here. The surface flaw column. So if you encounter a problem in tabular form like this, what that means is that when you're wanting to look at a conditional probability, we are restricting our attention to just where F is actually true. So it's 10 divided by 40. Whereas the unconditional event of just defective is 10 divided by the 400. Because we're looking at just which ones, what is the probability that we're defective overall over both surface flaws and non-surface flaws. And so that's where we end up with 28 over, because that's all the defectives over the 400. So notice that the probability of D given F is not equal to the probability of D. They're not the same. So that means that they're dependent. So knowing that there's a flaw on the surface is changing the probability that the part is defective. So let's take a look at data 2, new data. So in this case, still the same type of table. There's still 400 parts. Let's say it was run another day. Some calibration was done, it was run another day. So this time, the probability of D given F, defective given flaws, again, we're still looking at the same place. Now it's 2 divided by 40. Now the unconditional probability of the probability of D, probability of defectives, now is 20 out of the 400, which is also 0.05. They're the same. Therefore, events D and F are independent. So what that means is that knowing that we had surface flaws did not affect the probability that the part was defective in Table 2. Finally, independence with multiple events. And so if we have several events, E1 up to EK, which are independent, they're independent if and only if. So remember the mathematical jargon with if and only if. It can go both ways. If the events are independent, then this statement is true down here. The probability of the intersection is equal to the product of the probabilities. Only if, so if this statement is true down here, then we have independence. Okay, so we did a quick introduction to independent events and how to check for dependence. A couple different ways you can check for dependence depending on steps 1, 2, or 3, which I said were equivalent. And that is the conclusion of the lecture.